Okay, I think we are online again.
Mm-hmm.
So just go ahead with the agenda, I think.
Okay, so
I'm sorry for the inconvenience.
no issues. It's best at the beginning. So now you hopefully see the agenda. So we'll discuss why we need concepts, what are they, how you can use them as constraints, how you can use them with functions, with classes, how to write your own concepts, and then we'll see some real-life examples. Although, well, concepts are quite new, so we don't have so many examples, we don't have so many real best practices. Well, we'll discuss about these a bit later. So first thing first, why do we need something like concepts? And here I ask a question. Did you see that I moved forward with the slides? I keep an eye on the chat in the meanwhile. So problem is that overloads, they don't scale. So let's say that we want to write a very simple function just for the sake of the example, so we can keep it short. We want to write a function that adds up two numbers. Well, we might want to add up integers. We might want to add up some doubles, and we have to write different overloads. So you might have a lot of types to support, and what are you going to do? I mean, it's tedious to write all of them, and although like writing a lot, usually it's not a real bottleneck when you write the application. Still, the verbosity is bad because it becomes difficult to maintain. If you have to change the logic at one place, well, you have to change it most probably everywhere. So obviously, this is not a good solution, and I haven't said anything new with that. So you might think that, okay, then we can use templates, and probably it's better because then you have to write one single implementation. That's good. You can add up your integers. You can add up whatever floating point you want, but you will just accept everything without any constraints. So in this example, we add up two characters. And what do you expect this to be? I mean, probably you know what it's going to be. But it's possible that you expect something completely different. It might be that you expect that instead of one character that is somehow summed up from A and B, you would expect a string. But then, well, you will be deceived because that's not the case. You might have some potentially unexpected behavior. And it's quite probable that's not what you wanted. So it would be good if we could constrain somehow these implementations. And actually, since C++11, we can forbid template specializations. So let's say that you don't want to allow that strings could be added up. So you say that the specialization with string is deleted. Well, fair enough. It will give you an error. It works, but it doesn't really scale. So if we go back to the first example with the overloads, it's pretty much the same problem here, just from the other side. There we had to write everything to be allowed, but here we have to delete everything that we don't want to allow. And that's, again, tedious. So you might say, what about type traits and static assert? Well, you could use static assert, and it works. Hopefully, you will have even some better error messages. I say hopefully because, well, we provide some part of the error message. So hopefully, we write something meaningful there. And this is better than the previous solutions, I think, because we have less overhead. We have everything at one place. But still, these requirements are hidden because it's still in the body. of this template function. It's not at the top. Well, in this case, it's at the top of the implementation, but that might not be the case all the time. And it's not easy to reuse it in a meaningful way. So it's still not, let's say, not the best solution here. Well, we could go into more details about how to use std enable, if, and sfin, but well, we don't have the time for that. And I mentioned in the beginning that I meant this to be a more beginner-friendly talk, and sfin doesn't really match that requirement. So the next step, we arrive to the concepts, which will pretty much save us in this situation, because you can write your constraint, your concept in a quite concise and readable way. We'll get back to the exact syntax later on. So you can say that you have this concept number, and it must be either an integral or a floating point. Now, if you know which std integral and std floating point are already concepts themselves, so this is a combination of concepts. I know this is not a good concept. You might think that, well, we'll accept not only numbers. I know, bear with me. It's for the sake of example for the time being. So you define this concept, and you can put instead of the type name this concept in the template parameter list. So you can already constrain in a very readable way your accepted types. So it is readable. You see that it's easy to reuse because you can put concept even like this concept number even in a separate header, and then you include it where you need it, and well, you just say that you need a number in your templates. It's very reusable. So therefore it scales well, and it makes your code much safer, because it will be easier to constrain what types you want to accept in your different templates. We are going to see exactly how that works. So we saw that what main problem concept solves and how they can help. And now let's see a bit more in detail, what are they? So C++20 has been a big release, and there are many small and useful things in it, but often we refer to it like, okay, it has 4 big building blocks. You have the ranges, and I think it was yesterday morning, Tina gave a very interesting talk on how you can rangeify your code. Then we have modules, and I think that tonight with Gabriel, we'll have a really interesting Ask Me Anything session, mostly about modules. We have coroutines, and finally, we have concepts. That's what we are talking about here. So concepts are an extension for templates, but maybe extension is not even a good term. I heard a talk from Bjarne where he said that, well, he was dreaming about concepts for decades, and he sees them more like a completion of templates rather than an extension. In any way, you can see them as compile time booleans to validate template arguments. And you might have seen this syntax where you say that template type name T, bool, concept, and then you have the name and the expression. Well, if you saw this, this is not the case anymore. It was in the technical specification of concepts, but when it got standardized, the committee moved into another direction because, well, they agreed that bool can be omitted, because if we all accept that it's always a compile time boolean, then we don't have to say that concept is a boolean. We just know it is. And even in the core guidelines that is a bit still based on the technical specifications, you will see names written in camel case, but with the standard, the committee moved into another direction. And if you have a look at the standard library, you will see more the snake case syntax. So concepts you can use to constrain your template arguments. You can constrain what kind of types you want to accept. And therefore, you might say that a concept can be used as a constraint. And we'll see that basically a concept is a set of requirements on the public interface of the accepted types. So concepts can appear at different positions. We'll discuss each in detail. For the time being, I just want to show you these different positions, and I use a function template for that. So it can come, as we already saw, in the template parameter list instead of the type name. We can use it as a type constraint. Often we call it like a shortened notation. You can use it in a requires clause that comes after the template parameter list. You can use some constraint placeholder types in abbreviated function templates that you will see. We use it as a concept name auto. I will detail why we need both the concept name and the auto. And you also have the trailing requires clause that comes after the CV qualifiers. So now that we had a brief overview, let's see 4 different ways to use concepts with functions. I want to remind you that if you don't like, if you disagree with this concept number because it's incomplete, it's not, let's say, not correct, I know, bear with me. We'll discuss how to fix it at the end. But it's something short and easy to use for the examples. So we have this concept number, and we say that we accept any integral or floating point numbers. And first, we are going to use the requires clause. So how does this look like? You have the usual template type name T part, and then we say we require that T, this T parameter, must model the concept number. So it comes after the template parameter list, and you can write here your own, well, whatever concept to be satisfied. But you can even combine concepts here. You don't have to use one single concept. You can write their combination. So basically, just inline the body of the concept number, and I put it there. It works. But you can put there more things. You can use type traits. You can use any Boolean expression or basically any compile time values with certain limitations that we'll discuss. And then the function calls are just as always, but with a bit better error messages. So this is a quite basic example. I put it here green when we try to add 2 and 3, because it works. And the second one, this red one, it doesn't compile because 2 and 3.14, they are different numbers, and as they are different types. And as the compiler tells us, well, these types are conflicting for the one single parameter T, so it doesn't compile. This might be a quite simple example for showing that error messages are quite readable, more readable than before, but later during the presentation, you will see some other error messages, and you will see how much detail the compiler gives you, how it couldn't satisfy certain constraints of given concept. Then we move to the trailing requires clause, when the requires clause comes after the CV qualifiers. And apart from that, it's the same as the normal requires clause. There is no big difference here. But I have to mention, it's true for the requires clause and for the trailing requires clause, that this supports the combinations of different concepts and constraints and multiple parameter types. Because in the previous example, when we tried to add two, so an integer and a double, we saw that it didn't compile. So if you want to make it compile with those numbers, then you have to make sure that you have two template parameters which are of different types. But this is not new. It's not introduced by the concepts. But what is important, that with the requires clause and trailing requires clause, you can support that. But with the constraint template parameter, when you put, instead of the type name, the concept name, it's a bit different. Okay, so you have no more requires clause. That's why we also call it shortened notation, because it's simply shorter, because we just simply replace the type name. And you can still have the multiple parameters, but what you cannot have is the combination of concepts. You cannot write here that, well, I accept any t that is either an integral or a floating point. It is not possible. You must use here a named concept. And that's also the case for the abbreviated function templates. So here, you don't even have the template parameter list. You simply write concept name auto, and you can use it for the return value as well. That's something you can also constrain. So no requires clause, no template parameter list. It's very concise. And you have to say concept name auto. You have to write concept name auto in the parameter list, because otherwise you have no idea if you expect there, like whatever type or a concrete type, you don't know if it's a function template or a normal function. That's why you have to use both the concept name and the auto. And I refer to the core guidelines wherever it is possible, wherever it makes sense. So we should use in function templates whenever possible concepts, because it documents our code already. It documents what kind of types do we expect. It makes it safer. It makes it more maintainable. And in this case, unlike for the previous examples, the parameter types can be different. So before, when we said like, okay, t must be a number, and then you just use the t as a parameter type, well, for all the parameters, you needed the same types. Here, they can be different. In fact, here you cannot really say that A and B must be of the same type. And again, here you cannot write an expression instead of the number, a complex expression. So how do you choose among these four different ways? Because that's a lot. So if you have a complex requirement and not in a named concept, then you choose requires or trailing requires, where you can write completely what all your constraints. If you have a simple requirement, then use the abbreviated function templates. That's what the core guidelines also suggest to us. Well, if you have a simple requirement, you want to keep it short, and you want to control that the binded types of the parameters are the same. So, for example, both numbers should be an integer. Then you can go with the shorthand notation with the constrained template parameter. You might ask, well, are these different, or are they the same? And I use CPP Insight to look under the hood, and they are pretty much the same. So you see that add requires close is the same as the add constrained template, the shorthand notation. It compiles to the same code. And when you use the trailing requires close, it's almost the same. For some reason, we saw the trailing requires close even after running the CPP Insight, but this doesn't make any difference to the code. There is one expected difference, though. It's with the abbreviated function templates. You see that here you have two template types, whereas previously you had only one. And you have two even if they are the same, because the number auto A and number auto B, they are handled as two different template types. So this is the only difference, but this is something we expected. Now let's see how to use concepts with classes. So we have a bit fewer syntactical choices because, well, abbreviated function templates are for function templates. They wouldn't really make sense here. And we can use the trailing requires clause only in certain circumstances. We'll see. But when you want to use a concept, when you want to constrain your class itself as a whole, well, it doesn't really make sense there to use a trailing requires clause. Well, one, it's impossible. Second, why would you put it at the end of possibly a long class? So what we have is the requires clause. You can see here that it's something that we can use pretty much the same way as for function templates. It comes after the template parameter list. So here we have our wrapped number class, which has this template type T, and we require that T must model the concept of a number. So it's fairly simple. And again, here you can write any complex expression that you want. You have also the constraint template parameters available for you. So if you want to write something shorter, something even more readable, then you can omit the type name, and instead of the type name, you can put the concept that you want to model. That's very, very nice. But here you cannot use complex constraints. For that, you must use the requires clause. And then we are going to use a bit the trailing requires clause, because you can overload your functions in a template class by constraints. So let's say you have this class myNumber, where we have a templated parameter T, and here we provide two implementations, two overloads, if you like, for the divide function. One for integrals and one for floating points. So this comes quite in handy when you want to specialize your template class's behavior based on some type characteristics, type traits. And I have an example for that. It's a bit longer. I hope this is still readable on your screens, but here we have a simple concept car. It requires that the type that models the car concept has a start engine and an open door methods. And we have another concept which is based on the car concept in a sense that it uses it and it adds some additional requirements, like if your car is convertible, then it should have an open roof method. And then we have this class template for the vacation driver who wants to be able to cruise with his or her car, and only if this type C, which should be a car, okay, if it's also a convertible, then you should be able to open the roof. So then we have an SUV, which, well, it's not a convertible, so it only has the open door and the start engine functions. And when you try to call open roof on this VD vacation driver here, then we get compilation error because, well, we have an invalid reference to this function open roof. It's not part of vacation driver SUV because is convertible, is not modeled by SUV. So now let's see how to write our concepts. We're going to start with a simple concept, probably with the simplest concept that you can imagine. We call it any because it accepts any type, because it's always evaluated to true. So what did we do here? We listed all the template parameters. Well, in this case, only one. And then after the keyword concept, we put name, a meaningful name. In this case, it's any. And then we list the requirements. Here we have none. That's why we put only true there. So what kind of requirements can we express? Because as you imagine, we want to express more than simply true. We can list our expectations on the public interface. We can list our syntactic requirements, but when you write good concepts, and I think our community still tries to figure out what good concepts are, because one, we don't have the experience with them. Two, it's hard to make a concept right at the first iteration. You want to express also semantic requirements. And that's something that the core guidelines already suggest us, that we should avoid concepts without meaningful semantics. So I put here another example where we have some, let's say, clear syntactic requirements, but the semantics are not really there yet. So still, we tried to write this concept car where we have an open door, a closed door, start, stop engine, we can accelerate, we can brake, and then we have a tank. Well, I didn't put here the implementation, but you might imagine that the tank has a door, so you can open it and close it. Well, I never drove one, but I imagine you can definitely start its engine and stop it. You can accelerate and brake with it. So when you want to make sure that what we want to test whether a tank models a car or not, well, it will work. It will model it, but we can agree that this is not the best concept because a tank is not really a car. So syntactics are important, but semantics should be also important when you try to write a good concept. What we can do is also to combine already defined concepts. That's what we do in our concept number. We try to combine integrals with floating points. So we accept both integrals and floating points in the concept with the concept number. And the core guidelines suggest that whenever it's possible, we should use standard concepts. It's pretty much the same logic, I would say, that for the standard algorithms goes, because, well, these concepts are well taught through, well, at least much better than the concept that we would write right now. They are well tested. They are tested by the whole community, and they are simply better. Just like most probably an algorithm will perform much better, much more reliable than a raw loop that you would write yourself. So we can also combine, obviously, user-defined concepts, just to mention, and we can use them in any logical combination. You see here a small asterisk. I say any, but well, there are some things to consider. So what does combining concepts mean, and what are those things that we have to consider? So the and or, so conjunctions and disjunctions are definitely okay. You can free to combine concepts. You can combine Boolean literals, expressions. You can use type traits. You can use another requires expression within a concept. We'll see how to do that. But you have to pay attention when you want to use negation. With negations, it comes a bit tricky. So what does the exclamation mark say to us? So for Boolean expressions, you would expect that, well, whatever is in your expressions, all the sub-expressions should be well formed. They should compile, they are compilable, and well, they might return false. And that's how you can use the negation. But for concepts, it's a bit different. Well, you might expect a false, but a false doesn't necessarily mean that it's evaluated as a Boolean to false. It might be ill-formed code. And still, the rest of the concept might still satisfy the whole expression. So what does this mean? Let's have a look at an example why the opposite of true is not necessarily false as we imagined, as we thought about false before. So here we have another template function, foo, and it has two parameters, t and u, and in our requires clause, what we say that either t should have a blah nested type that is unsigned integral, or u should have this blah that is unsigned integral. And then, okay, we just have a class here where we alias this unsigned int with the name blah, so we can satisfy the requirement. And we pass also 42, a plain integer, to this compile. It compiles because whatever you put here in the requires clause, it doesn't have to be compilable. So when you pass in my type, well, it does have a blah, which is an unsigned integral. And then we pass in 42, which we put here instead of the u, but it doesn't have obviously a blah. So this wouldn't even compile. Yet these requirements are satisfied. So we can expect, let's say, usual Boolean false here. It's possible if we cast explicitly to bool, or with another way that I'm going to show. So one way to require that both T and U should have a blah, and one of them should be an integral, is to cast this expression explicitly to bool. As we discussed with people who joined the book fair for the C++ concepts book, we discussed that this is quite, let's say, implicit. You have to really understand this behavior. You have to know what does this cast mean there. It's not very readable. So you have a bit more verbose, but more expressive way to tell this. So we use a requires expression within the requires clause. Sometimes we call it as like nested requires, and we make sure that both T has this nested type blah and U has the nested type blah as well. So we have a conjunction here, we have an and, so both should return true, both should be true, and then it should be also true that one of these should be unsigned integrals. So I know usually we try to go with the shorter code, but here I think it's really worth to write it a bit more verbose, because what you have on the right side, I think it's much more readable than what you have on the left side. And now let's discuss how to find the most constraint before we go back to write our own constraints. So we have to say a few words on overload resolution. It's always the most constrained candidate that is the best. And a more constrained concept is based on another one. Like we saw with the car and the convertible. The convertible was more constrained than the car because it was already using the car, and it added some extra constraints. And when you have multiple different overloads with the same priority, then the compilation will fail because of ambiguity. And the compiler will always, automatically choose the right path based on the template parameter types characteristics. So here, once you see that we have an overload where we say that key should not be smart, in the other one we say that key should be smart. So this is not the way to go. You should not write this. And the core guidelines also reminds us that we should avoid these complementary constraints because it makes our code more brittle. So it's okay. In fact, it's not just okay, it's better to have a generic overload and a constrained one. You don't have to write the complement of it. But it might happen that you have more than 2 overloads. You have, let's say, 3 overloads or even more, and then the compiler will choose the most appropriate one. So here we write some constraints on the key in this class ignition. So we have a generic one. We have one where the key should be smart. We have another one where the key should be also smart and personal. And via subsumption rules, the compiler will choose the good one. Here, we don't have the time to go into details into the subsumption rules. If you want to read a good article in it, I would recommend you to go to Andreas Fertig's blog and check his article on subsumption rules. Here, I want to mention one interesting thing, that one interesting thing, that negation, again, it's with the exclamation mark, it can bring ambiguity. And if you want to rely on the subsumption rules because you have multiple overloads, you cannot simply use the negation, because the compiler tries to evaluate these expressions, these requires expressions, and it checks from where one originates. And well, while it could deduce that this smart key is the same as this smart key, but when it comes with a negation, it takes the whole, what you can find within the parentheses, it takes the whole as a new expression. For the compiler, the not smart key in the second overload and the not smart key in the third overload are something completely unrelated. Therefore, it's ambiguous, and this one wouldn't compile on the left. But on the if you want to rely on this, if you want to use such constraints, you have to name your concepts. You have to name the negated concepts, and you could write your concept not smart. Well, it would be, its body would be really simple. It would be what you have on the left side, so it's not a smart key. And then it can deduce that what you have in the second overload, not smart key, and in the third overload, they originate from the same place. Therefore, it can subsume them, and it can decide which overload it should take. If you are interested in more substantial rules, go to that article. I will share the link later on. So let's go back. How to write those concepts? How to write first some simple requirements on the interface. So what I call this is wishful writing. Just write down in the body of the requires clause what operations, what function calls do you expect to compile? What should be compilable? And in the parameter list of the requires clause, like it would be a function parameter list, you can just list all the types that you will need. And if you have some parameters, so we expect for this test concept that whatever type that satisfies it should have a method power that takes an integer as an exponent, you have to list that, okay, we'll need an exponent that is an integer. It's that simple. It's really just wishful writing there. You can write some requirements on the return types. We often refer to this as compound requirements. And basically, you can constrain the return types with two concepts that is shipped with the standard library. One is to convertible to, which takes two parameters from two, and the other one is stood same as. And then you can write your concept in a way that between braces, don't forget the braces, you put what's going on. You put sorry, I think I lost my mouse. So you put between the braces the function call, and then after an arrow you put your constraint return type. So in this case, you expect something that is convertible to an integer. If you are familiar with the technical specification for concepts that I think was released in 2016, if I'm not mistaken, you could use the bare types there. You could write simply as an integer, but right now you have no bare type for you cannot write bare types anymore because of future generalizations. You can express some type requirements. So you can express that a certain nested type should exist, something that we already saw with that blah example. You can say that a class template specialization should name a type, and you can do that also with alias template specialization. So we are going to see some small examples for each. For the nested types, you can say that, well, you require that this t : where you type should be a type name. Don't forget the type name there. And in the example, you can see that this compiles with a vector, because a vector does have a value type, but it doesn't compile for the integer because it doesn't have any member type. So the deduced initializer doesn't satisfy the constraints. That's the error message you get. I shortened it a bit, but it tells you that type name tt value type is invalid for an integer. So for nested template specializations, you can say something similar. You can say that in this case, we write a struct other that has a requires clause. And it says that its template parameter, it must not be an integer. And we just wrote a test concept called type requirement, which requires that other with t is instantiable. So when you try to use it with a character, it compiles fine because it's not an integer. But with an integer, it doesn't compile, because it tells you that other t is invalid because of the constraints are not satisfied. And it tells you exactly which constraint is not satisfied and with which types. So as we said in the beginning, the error messages are quite good. Then we can write requirements on the alias template specializations as well. Here, I couldn't really come up with a very meaningful example, so I borrowed this from the CPP reference. I can make sure that this template here, this template specialization, alias template specialization is meaningful, and or type models it. Well, this is also possible, but there are some more that you can model in a concept. You can nest requires clauses, but it's often an overcomplication. It's often just overcomplexifying things, but sometimes it comes in handy. So let's have this example. We have a struct droid, which has a clone function. And well, in coding, it often happens that we just copy paste some code, and probably that's what happened here too. So we have our droid v2, but we forgot to update the return type for the clone method. Then we have our clonable concept, and there, well, we require that a clonable type should have a clone function, and we also require, notice that we have an inner requires within the requires clause. We require that the return type of this clonable.clone should be the same as the type of the clonable. Well, this concept will catch the copy-paste error that we made. If you have a look at the last line of the main function, you will see that clonable auto C2 with droid v2, it would not compile because this nested requirement, it even tells us that it's a nested requirement, is not satisfied with droid v2. It's It's really a nice error message. It really eases our work to find bugs. But that nested requirement, again, it's overcomplication of the things, because we could have written simply that clonable.clone should return the same type as the type of the clonable. So often when you would use nested requires expression, it's really not needed. But in some cases, it comes in handy. So I just want to repeat the same example that I showed you earlier with the blah, because with the blah example, on the left side, you see that either you use a Boolean cast to make sure that both T and U has a nested type blah, but it's not really readable. It's difficult to understand, or you use some nested requires expressions within this requires clause, where you make sure that both T and U has the blah. It's more readable. So when you want to use, my message is that when you want to use a nested requires, think about it twice. Do you have an easier and more readable way to express it, or is it actually the way which is more readable? So let's go to some examples, real-life examples that we could use. So we used our number concept throughout the presentation, but the problem with it, well, you can approach it from different points of view. It obviously would not support user-defined numeric types, but if you just want to use the built-in types, the built-in numbers, then this is not good as such, because it accepts Booleans and characters as well. If you want to add up characters, well, if you call it the characters, it will add them up in one way or another. Or you can even add up Booleans, which probably you don't want. And when you use the concept number, its semantics really, it doesn't communicate that you want to accept their characters and Booleans. So we can forbid the unwanted types. No bools, no characters, which means that we keep our concept number as a basis for the new concept, and we add some new requirements. So it shouldn't be the same as bool, it shouldn't be the same as character, whatever. This is quite verbose, but it does the job, and most probably you will need it only once in your code base if you really want to constrain that your templates cannot be called with whatever that is not a number. And you will see that with the error message, you can easily see that if you call it, like say, with two Booleans, then your constraint is not satisfied, because you try to call it with two bools, and the concept explicitly said that T, the template type T, should not be the same as a Boolean. And it's evaluated to false, so compilation fails. Good. So now our number concept works here. And when it comes to utility functions in real life, what happens? Well, usually they just take any type. They don't have any static assertions. The template parameters are as bad as I used in this presentation for the sake of brevity. They usually just T, U, and so on. And well, in most cases, there is no documentation. So in our code base, I found something like, well, not even like this, because here our template parameter is called like some business object, but we had a similar function template. So it encodes some stuff you have this template parameter, but you don't know what it should be. You don't know what it could be. And then you have to dig deep into the code, and well, you have to investigate. It takes a long time, and it definitely takes more time than it should. So you can turn these poorly documented functions into self-documenting code if you don't use the naked T's. So you use good template parameter type names. And if you don't use any more unconstrained type names, because now you can specify concepts for all the template arguments, and that's something the core guidelines advocates for. So in our example, we can define a new concept. So let's say a business object with encodable stuff. Well, whatever the body here is not interesting. So what matters here is that we document what we expect from a type that could be passed in for our encode function, and then we can use that concept in our encode abbreviated function template here. And even if you don't want to name this concept because you will not use it only once, but only once, you can use it in a requires clause, maybe in a nested requires clause. You can see it that we have requires twice after the other. As Andreas Fertig said yesterday in his presentation, it's often a code smell, but sometimes it might make sense because it just means that you don't want to use a named concept, and you have to repeat the requires for that, because you cannot use the parameter in an unnamed context otherwise. And now again, you have a utility function that is well documented, because at the top of the function, at the signature level, you document exactly what kind of types do you expect, what kind of types this function accepts. So I think it's much better than writing a documentation, because this one, well, it's enforced at compile time. I don't have the time to bring more examples. I will share some links after for another interesting one. So let's jump to the conclusion. The key takeaways here are that concepts, they can help validate the template arguments at compile time, and they provide a reusable and scalable way to constrain your template parameters. And the standard library already gives dozens of generic concepts. In fact, it gives like about 50 concepts in 3 or 4 different headers, like in the header concepts, ranges, and I think the iterators header. There are plenty of ways to define our own concepts. You can really model any constraint that almost any constraint that you can imagine. We saw the different ways to do that. And I'd like also to share a call to action with you. So as soon as you switch to C++10, start using the concept, because it brings templates closer to all the developers, because it's so readable, it's so easy to write, and it makes your code safer. Use them for your applications, for your pet projects, if you cannot use C++20 at work, so you can already practice with concepts. And even if you don't have C++20, one thing that you can already practice is that you can already use good template parameter types. You use no more naked T's. And with C++20, you don't use naked type names either, because you can constrain all the parameters. Thank you for attending. that's for it. I'm not sure if we have any time for questions, but I'm ready to jump into the discussion room.
Yeah, thank you, Sandor.
Cannot hear you, Jörn.
You cannot hear me.
And I should be fine, I think.
Yeah?
Yes.
I hope the others can hear me.
I think so, because I think it was a problem on my side.
Okay, so we are really running out of time because Jens is giving a talk, and it's in 5 minutes, and so please join Sandor at the discussion table in the launch, and I hope you enjoy the next talk about meeting C++ update from Jens. And thanks again, Sandor, for the nice presentation.
Thank you, everyone. Thank you, Jörn. Thanks for the possibility.